Hi everyone, my name is Helena Bales and I use they, them pronouns. I'm a software engineer at Pivotal and I've been working on Gemfire for about the last 2 years and I've been a Geode committer for about 1.5 years. Today I want to talk to you about Geode's performance, specifically what the performance is like right now, how it's measured, and how we can improve it. So let's start with the most basic of those 3 questions, which is what is the performance of Geode? Here it is. So this is Geode's performance. On the vertical axis, we have the throughput in operations per second. On the horizontal axis, we have 4 tests that we are going to be focusing on today. We can see that partition get benchmark had an average throughput of about 200,000 operations per second. But what does that mean? 200,000 operations per second, just a plain number, to describe the performance of Geode doesn't really tell us much. It just raises more questions, like, is 200,000 a good number to have? Is the measurement consistent and accurate? And has it improved since the last version or gotten worse? And perhaps most importantly, can it be improved? Here are my answers to those questions from when we started making these new benchmarks. And we had pretty good performance. This is for version 1.9. But we were seeing some variance between runs, and we had some issues with stop-the-world garbage collections occurring. We also saw improvements from the previous version, and we had a lot of room for improvement. But this raises one more question. How do we know any of this? And that brings us to discussing how we measure performance in Geode. Oops, went backwards. Here we go. All right. So to answer that, let's start talking about our benchmark tests, how they currently are today. So when the performance team started replacing the previous bare metal benchmarks for Geode, we had several goals for the project. These are the goals that we've accomplished so far. The benchmarks can be run on demand against any version of Geode released or in development, on an AWS cluster or on a dev machine. And they can also be run from Concourse CI pipelines, or any script really. We also enabled running with a profiler attached for use in debugging performance bottlenecks. And finally, we can compare 2 runs of benchmarks for change in performance. We do still have a few goals that we want to accomplish. We're still working on these ones. So we want the benchmark to be run by members of the Geode community, you all. And so far, we've not received feedback that, that anyone has done so outside of our office. We'd also like for members of the community to add their own benchmarks. So if you have something that you want to test specifically, that's something that you can add to our existing tests. And the visualization of data is also something that we're still working on. It takes a few iterations to get that right, so that's not really surprising. And finally, we'd like to increase the test coverage of benchmarks over Geode. This is our current list of tests. We have a few. We're going to be focusing on 4 of them today. And those are replicated get benchmarks, partition get benchmarks, replicated put benchmark, and what was the last? Partition put benchmark. And we're focusing on those because gets and puts on replicated and partitioned regions are one of the most commonly used and basic operations that Geode supports, so it shows performance pretty well. With those tests, we also provide a variety of configuration options for running the benchmarks. So we currently support running with or without SSL enabled, running with JDKs 8 through 13, with or without security manager enabled, and with a wide variety of garbage collectors. Oh, and adjustable max heap size. Since these options change the behavior of the Geode cluster, adding these actually gives us more test coverage, which is great. So now let's move on and talk about how we can actually improve performance now that we all have a shared understanding of where benchmarks approximately are right now. And the first step to fixing a performance bottleneck is to find the performance bottleneck. Here are some of the things to look for using a profiler, including both monitor and reentrant locks, extra allocations, and garbage collections. Other things to look for are overuse of synchronization, getting a system property in a hot path, lazy initialization of objects in a hot path, and synchronization on a container such as a hash map. And I'll go over some of these examples in a bit. So now let's dive into a specific example of a refactor that we did, starting with the reason that we thought anything was wrong in the first place. When the benchmark was run, none of the resources were saturated. And when we ran the profiler, it didn't show us any hotspots, so we had no idea why. Eventually, we found the secret profiler option that shows zero-time reentrant locks and found that thread.park became a hotspot. And its callers were reentrant lock and the connection pool. So eventually, we found that the connection pool was holding a reentrant lock in a hot path while accessing a deck, also called a DQ or a double-ended queue. So this graph shows the scaling of performance by number of threads. So number of threads on the horizontal axis, throughput in operations per second, again, on the vertical. And as you can see, we've got a nice little dip in performance after 32 threads, which is not what we would hope to be seeing on a 36 vCPU instance in AWS. So this shows that we clearly have a bottleneck in the connection pool, which was what we were seeing before, and that's causing a decreased performance at higher thread counts. So this is our profiler result when we profiled the connection pool, and we found that we have a few hotspots here. Every operation that's executed on the server results in one call to borrow connection and one call to return connection. Both of those methods require a reentrant lock. This lock is responsible for almost half of the time spent in the execute on, or in both borrow connection and return connection. And that makes up almost all of the time, those two calls that we spend in execute on server. So this is the cause of the taper in performance that we were seeing. Oh, and borrow and return connection are highlighted in green, and reentrant locks highlighted in light blue, with our main caller execute on server in dark blue. So here's the issue in code. This is a pared down version of the connection manager impl, which implements the connection manager. The first arrow here highlights that we are storing available connections in a deck. Because a deck is not a thread-safe structure, the second arrow highlights that reentrant lock that we were seeing in the profiler, which is held every time that we access that deck. And while I go through, I'm going to show a lot of graphs and a lot of code snippets. I'm going to try and tell you everything that is relevant about that. So try not to get too focused on the individual lines of code here. So I'm going to focus on the borrow operation when we're talking about this issue, but we also see the same issue in return connection. So just keep in mind that this is for both of those methods. We also have two implementations of borrow connection, one of which takes a connection to a specific server and returns a connection to that server. The other one just takes a timeout and returns a connection to any available server. And that's the one that I'm going to be focusing on here, because it's a little bit of a simpler implementation. So this is the borrow connection method. The red arrows on the left highlight that a lock is held for a significant portion of this method. Note that this is also a collapsed version of this full implementation. So we're holding the lock even longer than it looks like we are in this. Holding the lock for this long makes it difficult for multiple threads to access the connection pool concurrently, and that's why we're seeing that taper at 32. The other issue here is that we have an await in this code. Awaits cause threads to be paused until the condition has been met and a signal is received. During this time, the lock is returned, which means that in order to resume that thread, we have to reacquire the lock, which means that we have to go to the back of the line again. So during this time, we get further delayed in returning a connection to the caller. And in the worst case, we're delayed by the duration of the timeout plus the duration needed to reacquire the lock under contention. So that can be a significant portion of time. So let's move on to how we solve this problem. The first part is to replace the deck in the connection manager with something else. In order to introduce some modularity into the code, we decided to pull out everything related to the available connections into its own class called the Available Connection Manager. This allows us to get rid of the the lock in the available connection manager as well, or in the connection manager initial implementation, due to the implementation of available connection manager, which I will show you right now. This is the signature of the class, and we have a deck that is replaced by a concurrent linked deck. The linked nature of this deck does provide some performance hits because it requires allocation and garbage collection of nodes, but the structure relies on compare and swap, so we have a lock-free implementation now, making the concurrent linked deck an ideal structure for this particular implementation with high contention. With that change in mind, this is what borrow connection looks like now. And this is still in the connection manager, not pulled out into the available connection manager. So there are no locks in this method. Instead, we call use first on the available connection manager with a predicate, if needed, to get a connection to the server that we want. And this is the implementation of use first. There's still no locking in this method, and remove first occurrence is thread safe, meaning that with a sufficiently large pool of connections, scaling should continue well past 32 threads. So now let's go back to another profiler view, and this is the profiling the changed code. So if we look at this now, we see that there are no longer any blue highlighted reentrant locks, and we have both the borrow and return connection highlighted in green again, and they're each spending only 1% of the time or 0% of the time spent within execute on server in those methods. So this provides pretty good confidence that that implementation didn't introduce new hotspots. The implementation of connection manager impl and available connection manager have been thoroughly tested at every level. I'm sure most of you have heard of unit and integration testing and are kind of familiar with those concepts. But we also tested this in 3 other ways. I'm going to start with distributed tests. And distributed tests are how the connection manager, or show how the connection manager behaves in a real Geode cluster. So we spin up a few servers and a locator, and in different VMs, and operations are run, causing the connections to be created, destroyed, borrowed, and returned. The next type of test is a concurrency test. This type of test takes an executor and uses that executor to run several threads, which puts pressure on the connection manager in order to test certain timings to make sure that we don't have any concurrency bugs. The final type of test that I want to talk about for this one is the performance testing, which is what we've been talking about this whole time. So let's see the results for that. This is comparing the commit just before the refactor with the commit of the refactor. We saw a 230+% increase in the performance and the throughput of partition get benchmark. So now that makes our 200,000 look like slightly less good of a number. And with this run, the CPU of the client was saturated, so we were able to actually use all of our hardware. So we also did a similar test to the one that we did before the refactor, where we looked at how this code scales with number of threads. And as you can see, 32 is right in the middle and still looks like fairly low throughput. And we're able to scale up to 256 threads before we even start to see it slow down. So that's pretty reassuring as well. And this is for Geode 110, which actually includes a few other small refactors as well, which gave us some great performance improvements in addition to this really big connection pool refactor. And with that, I want to move on to some other types of bottlenecks, starting with overeager allocations. And what I mean by this is that we are allocating an object long before we need it. And that results in excess garbage production. So once again, ignore most of the code here. There's a lot there. And let's focus on the highlighted areas. Specifically, the first yellow highlighted area is the declaration of attempted servers as a hash set. The second yellow highlighted area is the first usage of that object. And you can see in green, between those two, an early return. So that means that there is a possibility that we will construct the object and then return before we ever get to use it, which means it is just garbage. So, also, because that we are allocating a hash set, we're actually allocating two objects, both a hash set and a hash map. So lots of garbage here. And how do we fix this? Well, allocate closer to where it's used. Especially if you have an early return, try to allocate after that early return so that you're not just creating garbage for the sake of garbage. Another bottleneck I want to talk about is knowing your structures. In this example, we are using a linked list, and linked lists require that nodes be allocated and destroyed for each call to borrow connection and return connection. This is looking at an older implementation of the connection pool, which is a hot path. So that means that for each operation, we are both allocating a node and garbage collecting that node. So we can be more efficient than this because we can use a deck. And since the connection pool is of relatively constant size, the deck will not need to be resized very often. And this shows the importance of to performance of understanding your data structures and what's happening on the inside of them. So to wrap things up, let's talk about how much performance has improved. This is a graph showing the throughput for the 4 tests that we've been looking at for version 1.10 compared to version 1.9. Each of these tests showed a significant improvement in the performance due to the connection pool and the other refactors that I mentioned. Leave that up there for a minute if you want to look at the numbers more. And then here's a similar graph for latency. It also shows that we have a reduction in latency across these 4 tests between versions 1.9 and 1.10. So why should you upgrade Geode? You know, it takes a lot of work. And I think this is a pretty compelling argument. This is comparing 2 runs of Geode. The lower line is version 1.9, and the top line is version 1.10. And while you may see very different numbers on your cluster due to configuration changes, like differences, hardware differences, whatever that may be, but you should still see a very big jump in performance between version 1.9 and version 1.10, and this is for gets. So I think that's a pretty compelling version to upgrade your Geode cluster. And finally, I would like to leave a few links for you. First is the Geode repository, which I'm sure you're all familiar with, been to at some point in time. The next is the benchmark repository, and we would love for you to add benchmarks or run benchmarks. And then finally, the last link is a Jira query, which will pull up all of the performance bottlenecks that we found over the course of these explorations. And we haven't been able to prioritize them, but we would love for you to look at them and potentially submit some pull requests. If you're interested in performance issues, this would be a great way to get started. And that's all.
Cool. Questions? Anybody?
Which profiler did you use?
We used YourKit for this.
Question was which profiler?
Oh, yes. Sorry, I will restate the question.
I have to repeat it so it gets recorded.
Yeah. Any other questions? So the question was, how many servers are we using for our tests? For, I think all of the graphs that we showed here were 1 locator, 2 servers, and a client.
Yes. Question over here.
For overeager allocations, did we use any static analyzer tools or did we just profile? And for those, we were using, YourKit can do profiling of garbage collection as well as locks. So we were using the garbage collection and allocations sections of YourKit for that.
Is there a particular configuration that actually reduces the performance?
Sorry, I missed the second part of that.
That reduces the performance where you see that the particular configuration is not giving you performance highlighted.
Oh, so are there some configurations that show lower performance? Yes. I mean, there are a lot of ways to configure your Geode cluster poorly, and I know that configuration is a huge point that we talk about a lot with Geode. We haven't thoroughly tested every configuration because there are a lot of them, and we're just getting started with this effort. So if that's something that you're interested in, I highly recommend playing around with benchmarks some. It can be pretty fun to look at.
And are these benchmarks published somewhere that somebody can compare, like what configuration you tested?
Yeah, so the question was if these benchmarks are published anywhere, and they are found in that second link on the link slide, and slides will be available after this. So, did I see some question over here?
Hi. Hi. Well, I'm wondering at version 1.9, you already had great performance, seemingly. What prompted the question to optimize further?
So it actually started because we were making these benchmarks, or replacing our bare metal benchmarks. And when we were doing that, we just couldn't figure out why we weren't seeing any hardware saturated. And so that made us look at where the bottleneck might be. I think it was just really the fact that we were creating these benchmarks and we wanted them to be saturating our hardware, because otherwise are we really testing the performance of Geode? And so in order to really properly test, we had to deal with these issues.
What tools did you guys?
Oh, sorry.
What tools did you use for distributed and concurrency testing?
Both of those are written in Java. I don't know a ton about the internal workings of distributed tests, but I think the Geode panel would be able to answer that question better than I can. Or come find me later and I'll look it up for you.
Impressive results. Congratulations. Could you talk a little bit about the differences in performance improvement between the partitioned and the replicated, and why you saw better performance improvement on one versus the other?
Briefly, I can talk about that. I think that's another one where I'd be better off getting back to you. But those are very different code paths in Geode. So beyond that, let me do more research and get back to you on it.
Hi, but thanks for your presentation, and it was a great performance testing results. My question is there a performance difference in scaling horizontal versus vertical on the system resources?
We have not thoroughly tested horizontal scaling yet because we've been focused on getting that thread count up. So we'll see. To be determined.
Okay, thanks.
Hi. Do you have benchmarks on the clients?
So we aren't yet benchmarking clients since in Geode, other than using like the clients that we put out. They're sort of separate products, basically. So we've really been focusing on the Geode side of things. And the client that we use is what does the benchmarking.
Kind of hard to see the hands from here, but anybody else?
Have you compared these benchmarks with other products like Redis or Ignite?
So we are intentionally not comparing because it's hard to tell if that comparison actually means anything. Everyone runs their benchmarks differently, everyone's running on different hardware, and it's comparing apples to oranges often. So we haven't done that yet. We haven't figured out how to make that comparison actually mean anything.
Anybody else? All right, a lot of good questions on performance. Not surprising for a caching product. So thank you, Helena.
Thanks.